Welcome to The Explainer. Today, we are going to crack the code behind the strange and, let's be honest, pretty fascinating world of curved mirrors. You know the feeling, right? You've seen it in a funhouse, in your car's side mirror, or even just looking at your reflection in a spoon. The image is weird. It's warped, stretched, or totally shrunken. So what's the deal? I mean, how can one type of mirror give us a clear, predictable image like you see here in this lab setup, while another one creates just total chaos? What's the secret sauce? Well, it all comes down to one simple thing: the curve. These are the exact mysteries we're going to solve today. Why does your reflection sometimes look stretched out or squished? Why do things in your car mirror look so tiny? Can you actually focus sunlight with a mirror? And is it possible to see yourself upside down? We're going to uncover the simple physics that governs it all. Okay, let's dive right in. Believe it or not, every single reflection, I don't care if it's a flat mirror, a funhouse mirror, or a giant telescope, they all play by one single unbreakable rule. It's called the law of reflection, and it's super simple. The angle that light comes in at is the exact same angle it bounces off at. That's it. That law is the key to everything. But the real trick, and where all the magic happens, is figuring out how to apply that simple rule to a surface that's, well, curvy. To measure those angles, we need a reference point. So we draw an imaginary line that's perfectly perpendicular to the mirror's surface, right where the light hits. We call this line the normal. Now, on a flat mirror, this is a piece of cake. All the normal lines are perfectly parallel, like train tracks. But what happens when we bend that surface inward? Suddenly, those lines aren't parallel anymore. Look at that. They all start to point in towards a single spot. They converge. And if we bend it the other way, bulging it outwards, whoa, the exact opposite happens. Those same normal lines spread apart, pointing away from each other. They diverge. And this right here, this is the whole shebang. Whether those normal lines come together or spread apart is the key. The shape of the mirror dictates where those lines point, and that, in turn, tells the light exactly where to go after it hits. So, let's take a look at our first type of mirror, the one that curves inward, also known as a concave mirror, and see how this all plays out. Because all its normal lines point inward, a concave mirror does something really cool. It takes parallel rays of light, say from the sun, which is super far away, and it forces them all to bounce and cross over at one single super intense spot. We call that the focal point. And boom, right there. That's the answer to one of our big questions. Can you focus sunlight with a mirror? You bet you can. This amazing converging power is the principle behind everything from solar cookers that can literally boil water to those giant satellite dishes pulling in faint signals from deep space. So, how do we know where the image will show up? Well, we can actually map it out. It's a neat trick called ray tracing. We just need to follow two simple, predictable light rays from, say, the tip of this candle flame. Where those two reflected rays cross paths, that's exactly where the image of the flame's tip will appear. Sharp and, as you can see, upside down. Okay, now this is where things get really interesting. It turns out there are two kinds of images. If the light rays actually cross paths in front of the mirror, they form what's called a real image. You could literally put a piece of paper there and see the image projected on it. But if the rays only look like they're coming from a point behind the mirror, that's a virtual image. You can't project that one. Check this out. When an object is pretty far from a concave mirror, you get that real upside-down image we just talked about. But if you move that same object super close to the mirror, something totally different happens. The reflected rays spread out. They diverge, and our brain, trying to make sense of it, traces them back behind the mirror, creating a bigger, upright, virtual image. That's exactly how a makeup or a shaving mirror works. All right, so that's the inward curve. Now, let's flip it around and tackle the other type, the mirror that bulges outward, the convex mirror. Remember how the normals on this kind of curve spread apart? Well, the light rays do the exact same thing. A convex mirror takes nice parallel rays of light and just scatters them. It makes them spread out or diverge so that they look like they're all coming from a single point behind the mirror. And here's the thing about convex mirrors. Because they always spread the light out, the result is always the same. It doesn't matter where you put the object, you will always get a virtual image that's upright and smaller than the real thing. And that shrinking effect, that's the whole reason we use them for car mirrors. You know that little warning, Objects in mirror are closer than they appear. That's because the mirror is shrinking everything to give you a much wider field of view. It lets you see more of the road behind you. And just like that, we've solved our car mirror mystery. So let's just recap for a second. We've seen how just changing the curve of a mirror completely changes what we see. Now let's look at the beautiful physics that ties it all together. It really just boils down to this, doesn't it? You've got two kinds of curves: inward curling concave mirrors and outward bulging convex ones. They both obey that one simple law of reflection, and between them, they explain pretty much every weird and useful mirror effect we see in our daily lives. And here's the really mind-blowing part. All of this behavior, where the image is, how big it is, whether it's real or virtual, it can all be predicted with this one single elegant equation. It connects the mirror's focal length, f, with the object's distance, u, and the image's distance, v. And don't just think of this as some formula you'd see in a textbook. No way. This is the actual design tool that engineers and scientists use to build real-world tech. We're talking everything from the massive telescopes that look at distant galaxies down to the tiny, precise mirrors that surgeons use in medical procedures. It really makes you wonder, doesn't it? If all the complexity of reflections can be boiled down to one simple rule and one elegant equation, what other parts of our world, things we see every day without a second thought, are also secretly running on a simple, beautiful code, just waiting for us to discover it?